Elasticsearch. Elasticsearch is a distributed, real-time search and analytics engine built on top of the powerful Apache Lucene library. It's designed to make sophisticated full-text search easy by hiding Lucene's complexity behind a simple RESTful API that uses JSON. Think of it as more than just a search engine, it's also a scalable document store where every field is automatically indexed and searchable. A quick tutorial, building an employee directory. To get a feel for how it works, the chapter walks you through creating a simple employee directory. Here are the key steps and concepts. Indexing documents. Storing data is called indexing. Elasticsearch organizes data into an index, like a database, which contains types, like tables, which in turn hold documents, like rows. Each document is made up of fields, like columns. You can index a document without any prior setup. Elasticsearch will create the index, type, and field mappings for you dynamically. Dynamically. Retrieving a document. You can fetch a specific document by its unique ID using a simple GET request. Simple search. Using the _search endpoint, you can perform searches. A light search can be done by passing a query in the URL like q equals last name Smith. Query DSL. For more complex searches, you use the query DSL, a rich language written in JSON. This allows you to build sophisticated queries, such as finding employees older than 30 whose last name is Smith. Full-text search. This is where Elasticsearch shines. A search for rock climbing will not only find documents with that exact phrase, but also documents that contain the individual words rock or climbing. It automatically scores results by relevance, so documents that are a better match appear higher up. Phrase search. If you need to find exact phrases, like rock climbing, you can use a match phrase query. Highlighting. Search results can include highlighted snippets of text that show exactly where your search terms matched within a document. Analytics with aggregations. Beyond search, Elasticsearch can perform powerful analytics. Aggregations allow you to summarize your data, much like group by in SQL, but far more powerful. For instance, you could quickly find the most common employee interests or calculate the average age of employees for each interest. Finally, the chapter emphasizes that all this functionality is built on a distributed system that is designed to be transparent and easy to scale. Chapter 2. Life Inside a Cluster. This chapter explains how Elasticsearch achieves scalability and high availability by distributing your data across multiple servers. Cluster, node, and shard. A node is a single running instance of Elasticsearch. A cluster is a group of one or more nodes that work together. Data in an index is split into smaller pieces called shards. A shard is a fully functional, independent search engine. Elasticsearch automatically manages the distribution and balancing of these shards across the nodes in your cluster. Master node. One node in the cluster is elected as the master. This node is responsible for managing the cluster, like creating indices or adding/removing nodes. It is not involved in document-level searching, so it doesn't become a bottleneck. Cluster health. The health of your cluster is indicated by a color. Green. All shards are allocated and everything is working perfectly. Yellow. All primary data shards are available, but some replica, backup shards are not. Your data is safe, but you have reduced high availability. Red. At least one primary shard is missing. This means some data is unavailable and the cluster is in a critical state. Primary and replica shards. Each shard is either a primary shard or a replica shard. When you index a document, it's stored on a primary shard. The number of primary shards for an index is fixed when the index is created and determines its maximum storage capacity. A replica shard is a copy of a primary shard. Its main purpose is to provide failover. If a node with a primary shard dies, a replica on another node can be promoted to become the new primary. Replicas also help with performance by handling read search requests. Scaling out. You can easily scale your cluster's capacity. Adding a node. If you add a new node to the cluster, Elasticsearch will automatically move shards over to it, rebalancing the load across all available nodes. Increasing replicas. You can increase the number of replica shards at any time. This allows you to handle more search traffic and increase redundancy. For instance, if you have an index with 3 primary shards, you can scale it to run on 3, 6, 9, or more nodes just by adjusting the number of replicas. Coping with failure. If a node goes offline, the cluster automatically responds. If the lost node was the master, a new one is elected. If the node contained primary shards, the cluster will promote the corresponding replica shards on other nodes to become primaries, ensuring that data remains available. Chapter 3. Data in, Data out. This chapter focuses on the fundamental operations for managing documents in Elasticsearch. What is a document? A document in Elasticsearch is a JSON object. It's a collection of fields, keys, and their corresponding values, strings, numbers, booleans, dates, arrays, or other objects. Elasticsearch stores these entire objects and makes them searchable. Document metadata. Every document has 3 key pieces of metadata that uniquely identify it. _index, the database where the document resides. _type, the table or class of object the document represents. _ID, the unique identifier for the document. Indexing, creating documents. To index the document with your own ID, you use a put request to a specific URL, put/index/type/ID. If you don't have a natural ID, you can let Elasticsearch generate one for you by using a post request to post/index/type/. Retrieving documents. To get a document, you use a GET request to its unique URL, get/index/type/ID. The original JSON you indexed is returned in the _source field. You can also retrieve just specific parts of a document. Updating and deleting. Documents in Elasticsearch are immutable. They cannot be changed. To update a document, you replace it by re-indexing it with the same ID. Elasticsearch marks the old version as deleted and adds the new one. To delete a document, you use a delete request. This also works by marking the document as deleted. The actual cleanup of deleted documents happens in the background. Optimistic concurrency control. To prevent losing changes when 2 processes try to update the same document at the same time, Elasticsearch uses a versioning system. Every document has an _version number that increments with each change. You can specify the version you expect to be updating, and if the document has been changed in the meantime, your update will fail, preventing data loss. Partial updates. The Update API allows you to make partial changes to a document, like incrementing a counter or adding a tag, without sending the whole document. Internally, it still performs the retrieve, change, reindex process, but it does so efficiently within a single shard. Optimistic concurrency control. To prevent losing changes when 2 processes try to update the same document at the same time, Elasticsearch uses a versioning system. Every document has an _version number that increments with each change. You can specify the version you expect to be updating, and if the document has been changed in the meantime, your update will fail, preventing data loss. Partial updates. The Update API allows you to make partial changes to a document, like incrementing a counter or adding a tag, without sending the whole document. Internally, it still performs the retrieve, change, reindex process, but it does so efficiently within a single shard. Bulk operations. Multi-get, mget, to retrieve multiple documents at once, which is much faster than fetching them one by one. Bulk API, to perform many create, index, update, or delete operations in a single request. This is extremely useful for indexing large amounts of data, like logs, very efficiently. The request format is a stream of JSON actions and documents separated by new lines. Chapter 4. Distributed Document Store. This chapter delves into the mechanics of how data is stored and retrieved in a distributed cluster. Routing a document to a shard. When you index a document, Elasticsearch needs to decide which shard to store it on. It does this using a simple formula. Shard equals hash, routing, % number of primary shards. The routing value defaults to the document's _ID, which ensures that the document is consistently routed to the same shard. This is why the number of primary shards for an index cannot be changed after it's created. Write operations: create, indexed, delete. These operations must be successfully completed on the primary shard first. 1. A client sends a request to any node, the coordinating node. 2. The coordinating node uses the routing value to determine the correct primary shard and forwards the request to the node holding it. 3. The primary shard executes the operation. If successful, it forwards the request to all of its replica shards in parallel. 4. Once all replicas confirm success, the primary shard reports back to the coordinating node, which then reports success to the client. This ensures your data is safely stored on multiple nodes. Read operations: get. A read request can be served by either the primary shard or any of its replicas. The coordinating node will round robin between the available copies of the shard to balance the load. Partial updates. A partial update combines the read and write patterns. The request is sent to the primary shard, which retrieves the document, modifies it, and then re-indexes it. Once that's successful, it forwards the new version of the full document to the replicas. Multi-document operations: mget, bulk. For batch requests, the coordinating node is smart. It figures out which shard each document belongs to, groups the requests by shard, and sends parallel sub-requests to the appropriate nodes. Once all the responses come back, it assembles them into a single response for the client. Chapter 5. Searching: the basic tools. This chapter introduces the basics of searching in Elasticsearch. The _search API. This is the main endpoint for all search operations. An empty search. Get_search empty simply returns all documents in the cluster sorted by relevance score by default. The search response contains a hits object, which tells you the total number of matching documents and includes the first 10 documents in a hits array. Each hit contains the document's _source and _score indicating its relevance. Multi-index, multi-type search. You can search across one index, multiple indices, example, the GB, US _search, or all indices, /all _search. You can also narrow your search to specific types. Pagination. To view results beyond the first page, you use the from, the starting document index, and size, the number of results per page parameters. Be careful with deep paging, as it can be resource intensive. Search Lite, query string search. This is a simple way to search by passing parameters in the URL, like get/search tweet equals Elasticsearch. It's great for quick tests from the command line, but is not recommended for production applications due to its limited and sometimes fragile syntax. The _all field. By default, Elasticsearch takes the string content from all fields in a document and concatenates it into a single special field called _all. A simple query string search without a field name specified will search the _all field, which is why a search for Mary might match a user named Mary, a tweet by Mary, or a tweet mentioning @Mary. Chapter 6. Mapping and Analysis. This chapter explains two of the most critical concepts in Elasticsearch: how data is interpreted, mapping, and how text is processed to make it searchable, analysis. Exact values versus full text. Exact values are things like dates, numbers, or specific string identifiers, e.g., a product ID. A search for these values is a simple yes/no match. Full text is human language, like the body of an email. Searching full text isn't just about matching, it's about determining how well a document matches a query, its relevance. Inverted index. To make full-text search fast, Elasticsearch uses an inverted index. This data structure contains a list of every unique word that appears in any document, and for each word, a list of the documents it appears in. When you search, Elasticsearch can look up the search terms in this index to quickly find matching documents. Analysis. This is the process of converting a block of text into a list of individual normalized tokens, words, suitable for the inverted index. It's performed by an analyzer, which consists of 3 parts. 1. Character filters. Tidy up the text before tokenization, e.g. stripping HTML tags. 2. Tokenizer. Breaks the text into individual tokens, e.g. splitting on white space. 3. Token filters. Modify the tokens after tokenization, e.g. lowercasing them, removing common stop words like the or a, or stemming words to their root form. Mapping. A mapping is the schema definition for a type. It defines the data type for each field, e.g. string, long, date, boolean, and how that field should be indexed and analyzed. When you index a document with a new field, Elasticsearch uses dynamic mapping to guess the data type. You can customize the mapping for fields. The most common customization is for string fields, where you can specify whether a field should be analyzed for full-text search or not analyzed to be treated as an exact value. You can also specify which analyzer to use. Mappings also support complex types, like arrays and nested objects. Chapter 7. Full Body Search. This chapter introduces the Query DSL, the rich JSON-based language for writing powerful and precise queries. Queries versus filters. A query answers the question, how well does this document match this query? It calculates a relevance underscore. Queries are typically used for full-text search. A filter answers the simple question, does this document match? It's a yes-no answer and doesn't calculate a score. Filters are very fast and are easily cached. They are used for structured data. General rule. Use queries for full-text search or any condition that should affect relevance. Use filters for everything else. Important queries and filters. Filters. Term. Find documents containing an exact term. Terms. Find documents containing any of several exact terms. Range. Find numbers or dates that fall within a range. GT, LT, GTE, LT. Exists/missing. Find documents where a field has a value or has no value. Bool. Combine multiple filter clauses with must, and, must not, and should logic. Queries. Match all, matches all documents. Match, the standard query for full text or exact value search. It analyzes the query string before searching. Multi-match, run a match query on multiple fields at once. Bool, combine multiple query clauses. It's similar to the bool filter, but also combines the relevant scores from each matching clause. Combining queries and filters. You use a filtered query to wrap a main query and a filter. The filter is applied first to narrow down the documents, and then the query is executed only on the matching documents to calculate relevance scores. This is a very common and efficient search pattern. Chapter 8. Sorting and Relevance. This chapter covers how search results are ordered and what relevance really means. Sorting. By default, results are sorted by the relevance score in descending order. You can sort by any field, such as date. When you sort by a field, the underscore is not calculated, which can improve performance. You can also do multi-level sorting, for example, sorting by date first and then by score. String sorting and multi-fields. To sort on a string field alphabetically, the field should not be analyzed. However, you still need it to be analyzed for searching. The solution is multi-fields. This allows you to index the same string field in 2 different ways. Once analyzed for searching, e.g., tweet, and once not analyzed for sorting, e.g., tweet.raw. What is relevance? The standard algorithm for calculating relevance is term frequency, inverse document frequency, TF-IDF. It considers three main factors. 1. Term frequency, TF. How often does the search term appear in the document? More is better. 2. Inverse document frequency, IDF. How often does the term appear in all documents in the index? More is worse. Common words like the are less important. 3. Field length norm. How long is the field? A match in a short title field is more significant than a match in a long body field. Understanding the score. You can add the explain parameter to a query to get a detailed breakdown of how the underscore for each document was calculated. This is invaluable for debugging complex queries. Field data. To sort on a field, Elasticsearch needs to load all the values for that field into an in-memory data structure called field data. This is fast, but can consume a lot of memory, especially for string fields with many unique values. Chapter 9. Distributed Search Execution. This chapter explains the process of executing a search across a distributed cluster. A search is performed in two phases. Phase 1. Query. 1. The coordinating node broadcasts the search request to a copy of every shard in the index. 2. Each shard executes the search locally and creates a sorted priority queue of its top results. Example, the top 100 documents if you requested page 10. 3. Each shard returns a lightweight list of results to the coordinating node containing only the document IDs and sort values, like the underscore. 4. The coordinating node merges these shard-level results to create a globally sorted list of document IDs. Phase 2. Fetch. 1. The coordinating node identifies which documents are needed for the current page of results. Example, documents 91-100. 2. It then issues a multi-get, mget, request to the relevant shards to fetch just those documents. 3. Once the documents are retrieved, the coordinating node assembles the final response to send back to the client. Search options. Preference can be used to ensure a user's requests always hit the same shards, which avoids the bouncing results problem where results change order between refreshes. Scan and scroll. This is the recommended way to retrieve large numbers of documents, example for reindexing. A scan search disables sorting, and the scroll API lets you efficiently pull batches of results until you have them all. Chapter 10. Index Management. This chapter covers the APIs and settings for managing your indices and data schemas. Creating and deleting indices. While indices can be created automatically, you can create them manually to specify custom settings and mappings. Key settings include number of shards and number of replicas. Configuring analyzers. You can configure built-in analyzers or create your own custom analyzers by combining character filters, a tokenizer, and token filters. This gives you complete control over how your text is indexed. Types and mappings. A mapping is the schema for a type. It defines the fields, their data types, and how they are indexed. The top-level mapping is called the root object. It contains the field properties as well as metadata fields like _source and _all. _source. By default, the original JSON document is stored in the _source field, which is almost always what you want. _all. You can disable this field or control which fields are included in it to save space and gain more control over search. Dynamic mapping. Elasticsearch will try to guess the data type of new fields. You can control this behavior with the dynamic setting, true, false, or strict. You can also create dynamic templates to define custom rules for new fields based on their name or detected data type. Reindexing your data. You cannot change the mapping of an existing field. If you need to make a change, the process is to re-index. Create a new index with the correct mappings and copy all your documents from the old index to the new one. Index aliases and zero downtime. An index alias is a pointer or shortcut to one or more indices. They are incredibly powerful. For re-indexing, you can have your application point to an alias, e.g., myIndex. When you need to re-index, you create a new index, e.g., myIndexv2, copy the data, and then atomically switch the alias to point to the new index, all with zero downtime for your application. Always use aliases in your application code. Chapter 11. Inside a shard. This final chapter in the Getting Started section looks at the low-level workings of a shard, which is really a Lucene index. Immutability and segments. An inverted index once written to disk is immutable. It never changes. This immutability allows for heavy compression, eliminates the need for locks, and makes caching very effective. To handle new or updated documents, Lucene writes new, small inverted indices called segments. An index, therefore, is a collection of segments. Deletes and updates. Because segments are immutable, documents are not deleted from them. Instead, a special .del file marks documents as deleted. When you update a document, the old version is marked as deleted and the new version is indexed in a new segment. These deleted documents are physically removed only when segments are merged. Near real-time search and refresh. Committing new segments to disk and fsync is an expensive operation. To make new documents visible to search quickly, Elasticsearch uses a more lightweight process called a refresh. By default, this happens every second. A refresh writes new in-memory documents to a new segment in the file system cache without an fsync. This file can then be opened for searching, making the new documents available. This is why search is near real-time. Durability and flush. To ensure data is not lost in a power failure, Elasticsearch uses a transaction log, or translog. Every operation is written to the translog before it is processed. Periodically, e.g. every 30 minutes or when the translog gets too big, the index is flushed. A flush performs a full commit, an fsync of segments to disk, and clears the translog. In case of a crash, Elasticsearch can recover any lost operations by replaying the translog. Segment merging. As new segments are created, they need to be periodically merged into larger segments to keep the total number of segments down. This process happens in the background. It's also when old deleted documents are finally purged from the disk. The Optimize API can force a merge, but it's rarely needed and should be used with caution, typically only on read-only, time-based indices. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.